are on the logistic regression. Wait a second. This is again an interesting topic, and it has a term regression, right? So you might be wondering, like, what is the connection between the logistic regression and the linear regression that we have just seen? All right. So, well, this is a model which we use for classification task, right? And we have just seen a regression, and probably you understand the difference between the classification and regression. Right? In classification, the target is concrete, right? Target is concrete, or discrete we should call, right? Discrete is a better term. Whereas in the case of regression, the target was continuous, like the cost. All right, the cost of the houses and all that. If you want to predict the height, or you want to predict some continuous value. So that was the example of a regression. But now we are interested in classification. And in classification, we want to give some label, right? Like the labels. Let's have a look at these examples. Assume that you're given some information related with social media, okay? And the gender is not revealed to you. Probably you are looking at the tweets, and from those tweets you need to make out whether this tweet is from male or female, right? So we need to put some label, male versus female. So this is discrete, just two classes possible, okay? Similarly, well, you may read about the sentiments of the people, the same idea, right? If I give you just the Twitter data only, and I'll say, okay, fine, from these tweets where people are expressing their political views, can we identify whether this tweet is from a person who's Democrat or a person who's Republican, right? Again, we are putting some label, Democrat or Republican. Similar way, you are given emails, and from that email you need to identify whether this email is spam or non-spam, right? Given the data which is about cancer, and from looking at that you need to identify whether the data that we have, does that belong to a person who is suffering from cancer or a person who is healthy, right? So ultimately, in the training data also, we will be given some label, and that's what ideally we want to predict, right? So when we are given a test data for which we do not know the label, we would like to give them the label. We'll say, okay, fine, this email looks like a spam, or this guy looks like a Republican. Okay, so that's what we have to do in classification. So label is a term which is applied to classification. All right. So now, how should we go about it, right? We have learned this model called regression, right? So we would somehow try to fit whatever we have learned to this problem of classification. Okay, so the straightforward solution to this problem is somehow to change the target, because there are only two classes involved: male, female, Democrat, Republican, spam, non-spam, cancer, benign. So one straightforward approach would be to label one class as 1, the other one as the 0, right? That's what we actually do for binary classification. So let's come up with this label, right? The data is given to us that we would consider for the first case. We will label all the female data record with 1 as the target. And for male, if we had the category, right, where male and female was written in our data, we would replace female with the value 1 and male with the value 0, right? That's how we will format our data. Same kind of thing we'll be doing for other data sets as well. Republicans 1, Democrats 0, spam 1, non-spam 0, cancer 1, benign 0. So here it depends, right? It is up to you whether you want to give Democrat as 1, Republicans as 0. It's up to us, like, what is it that we want to predict? Do we want to predict whether this guy is Democrat, or we want to predict whether this guy is Republican, right? So it depends on the problem that we are solving. Here we are interested in finding whether this person has cancer or not. So whatever you're looking for, that will become the positive, label, or you can label that as 1. Okay, so now once you have changed your label from text, we should not say text, right? Categorical data, right? Do we understand what is a categorical data? Data that has just categories, right? So here we will have 2 categories in the first example, male versus female. That's what we had in our original data, but we changed that to 1 and 0, but it is still categorical, but there are the numbers, right? 1 and 0. We can interpret numbers. And the reason why we are converting that to a number is that we know we have a tool, which is regression, right? And we want to use the same tool, the regression, for this task also. Okay, so our intent is to somehow use the data which is available to us and predict a numeric. Now, what will happen? Okay, let's think of a very simple scenario. We can pick any data, right? Let's assume that we pick this data about the first data, male versus female. All right, and we may assume, right? Let's assume that on x-axis, this is your x-axis, we have x is equal to height, right? X was height, and we applied the linear regression, and this is what we found, right? So we know how the linear regression model fits. Given the data, it will try to find the best line that would approximate that data, right? And that's what we found. All right, and we'll be happy with this result. Okay, fine, fine. We found the regression, and we will use it for the prediction. Now, there are problems associated with this kind of learning, right? There is a problem associated with applying linear regression for labeling. I think this is our class 1. This is our class 2, right? So its nature is such that it will pass through the middle of the data. It will cut between the classes. Between the classes it is cutting, right? And that might be one of the reasons why it is so much sensitive to the outlier. If you have one more outlier here, it will tilt this way. Now, if you look at the natural problem of classification, then we don't want that model to fit the data. What we are looking for is a boundary like this, right? We are looking for a line which could divide these two reasons, the reason of positive class versus the reason of negative class, right? So when we are attempting to classify, we are looking for a different kind of model, a model which could separate, right? So the classification model is a model which could find the region, okay, the region that belongs to the positive class, like this one, right? And the region which would belong to the negative class. Negative means a male here. Okay, so our see, what we're looking for in classification are regions. One region that belongs to the positive class, the other region that belongs to the negative class. Okay, so the natural thing that we have in linear regression needs to be changed. All right, we need to modify linear regression in such a way that we could identify this boundary, right, which is also called decision boundary. All right, so we are looking for a decision boundary, and that decision boundary, unfortunately, the linear regression cannot provide us because of its nature, because of the fact that it will try to pass through the data. All right, so from this thing that we had, we somehow want to make it to identify this line here, what we have in the green. Question? All right, so let's move on. Decision boundaries, right? That's what a classifier would be looking for. So look at this one, right? If you have these two classes, you could see the symbols, right? One is circle, the other one is red cross. The blue circle versus red cross. That means we have two classes, class 1 and class 2. Let me put C1 and C2. These are two classes. And when the data is given to me, then I would like to learn this decision boundary, right? And we are looking at the classification, binary classification. We can have multi-class classifications as well, where in place of 2 you can have 3 classes or even more classes. But we're to start the discussion with the simplest possible, that is the binary classification. So these are 2 classes. So the classifier that we would use would be the one which would come up with this boundary, right? Decision boundary. And this decision boundary will help me out. If I get a test point right here, this point, right? This is a new data that I found, and I'm not sure whether I should put here or I should put here, right? So as you could see that this happens to be on the right hand side of the decision boundary, right? And we know that all the data points for class 2, they happen to be on the right hand side of the decision boundary, right? So once I learn this decision boundary, I will classify it to C2. In place of that, if I had a data point here, test data, then this being on the left hand side of the decision boundary, I'll put that into C1, right? So this is what we are looking for in a classifier. Ideally, our 2 class will be well separated in feature space, so a line can partition them. So here we are looking at a very ideal scenario of the classes which are linearly separable. That's the great news actually. If you have your data as linearly separable like this, great, no problem at all. You can find a perfect linear classifier that will separate the classes into 2. But the life is not always so simple. You may have something like this as well. Assume that this is red, okay? So one of the classes right here, and assume that this is blue. This in fact is a blue, but not the same blue. So you should see that although you found this line which is classifying most of the samples correctly, but there are 2 samples which we see are not properly classified. Okay, so we may have in real life we may have some data points which may not be properly classified by our classifier. All right, and then we will evaluate the performance of our classifier using the measures that we have learned, right? Recall, precision, and all that thing. So what logistic regression does, this is a method to find the best separating line from the given training set. So logistic regression in fact finds out this line for us, which would separate the classes which will separate the class using the decision boundary, so that we could decide, right? So we'll have this notion of probability. So the closer is this, the farther this class is from this line, with more probability we would say that this belongs to C2, right? The more this data point is, or the more closer this is towards the decision boundary, will be low in confidence, right? The more you are on this line, our confidence would be low. So this thing you would see pretty soon. Okay, so now what I should ask is that if I have the points like this, right? So should I still continue using this linear classifier, or should I come up with this? Which one is better? Green versus this curvy one. We would stick to Occam's razor and we will prefer this one, because probably this is a good explanation. This is a simple explanation. Okay, let's move on then. What will happen, right? Continuing with this same discussion where the class was linearly separable versus the class which is not linearly separable, right? So let's see what we have in this picture. Now, well, we have 2 classes. These blue circles are W0, sorry, Y0, and then the red cross that we have is the Y1. Okay, now we do have a decision boundary, but this decision boundary is not linear. You can see that this is a circle, right? So this boundary is separating the 2 classes. The rule is that if your data point happen to be inside this radius, then it is class Y0. If that data point is outside the circle, then that is Y is equal to 1, which is the red cross. All right, so just the way we discussed the fact that, you know, for linear regression also, the um, the features that we have, we can change the features as well, right? If you remember, we were doing the linear regression and we figured out that, you know, we might have a scenario like this where the data is distributed this way, which doesn't look like linear. Remember, data is like this, which doesn't look like a linear, and we want to fit a model on that, right? So we did say that if we have just one feature x, and on that we are learning fx using linear regression, and the data doesn't look like linear, then we will try the combination of non-linear features, which means you will have x, you can also use x square, right? And then using these two, you can predict the target feature in linear regression. The same thing applies for logistic regression as well. So whenever your decision boundary is not linear, then in that case, we would use the features like x squared or x1 multiplied by x2. These are two different features, right? So we'll have to play with the features. If you just visualize how the data looks like, and accordingly, we will fix the features and can plug that into the logistic regression. So the same trick would be applicable for logistic regression as well. It can find nonlinear boundaries if we see it with the nonlinear features, right? So if you understand the equation of the circle, then, you know, you can figure out that it is quadratic too. So, you know, the same thing for you know, two classifiers. And these are two possibilities: classifier A and classifier B, right? So the question, right? I had a very not so good looking picture, but that was conveying the same information, which is about decision boundary, right? So it is all right for a decision boundary to have some errors, right? You can see here 1 point, 2 point, 3 point, 4 points. 4 points are misclassified by this decision boundary, but that is all right. Why? Because this is a simple decision boundary, whereas this decision boundary that you have in A is more complex, although there is no error because of this decision boundary, but, you know, it is overfitting the data. The chances are that these data points that you're looking at, right, these might be just because of the error. It's possible that these are just noise, right? So if you pay too much attention to each data sample in training, then what will happen? You may end up learning a too complex classifier, too complex a decision boundary, right? Which perfectly, you know, aligns with the Occam's razor concept. We will always prefer the simpler decision boundary. All right, so question. Now we did realize that, you know, sorry about, okay, good. We did realize that, you know, the linear regression we cannot apply for classification straight away. We'll have to do some fix in there, because what we are getting from linear regression is not a decision boundary. We are looking for a decision boundary. So how can we transition? How can we move from a simple linear regression to the logistic regression, right? So here is this function that we use, logistic function, for that, right? So before we get to the logistic regression, let's see like what is this logistic function one more time, right? Just for recap, you people know about it already. So this is the logistic function, which has this curve like this. All right, so it will cross the y-axis at the value 0.5, and that value you would get when the x is 0, right? Good. And then we know that this f means the sigmoid thing, right? This is our f is equal to 1 over 1 plus e to the power minus t, and the f is the function of t. All right, and we know that f of 0 is 1 by 2, and f of infinity is 1, and f of minus infinity is 0. That is how we define the logistic function. Okay, so now why should we use logistic function in our logistic regression? The reason being that, what do we need from logistic regression? Okay, so ideally we want these labels 1 versus 0. This is what we want, and that's how we changed our data. We changed the target to 1 and 0, like 1 for female and 0 for male, right? So this is ideally what we want to learn, but what we would learn in fact is the probability of 1. That's what we have to learn, right? So we can kind of think of this as the extreme probability in our labeled data, right? If our data is labeled as 1 in the training data, then that means with probability 1 it is female, right? And if the person if that data is being labeled as 0, then we know that with probability 0 it is female. Probability 0 it is female means it is male, right? So this 1 and 0 that we have in our data needs to be treated probabilistically, right? If you could think that way, then we can make use of logistic function into the linear regression, and we will come up with a model that is called logistic regression, right? So what logistic regression will tell us would be the value, the probability of the label being positive, or the probability that a given data point is female. Is that making sense? Right? So whenever we have to map some real value to the probability between 0 and 1, then this logistic function is a perfect choice, right? That's the reason logistic function is used in logistic regression, right? Everything would be linear regression only, but ultimately what will happen is that this will happen, right? So let me straight away take you to this slide. So what is it, right? Does it look familiar to you? What do I have in this expression? Do you all see that, right? If I give you the proper values of w, right? W vector, this is w vector, right? So what you will do using those values, you are all correct, right? This is in fact a line. Fine, yeah, this is a line, right? And why is this a line? Because this is the line that we learn after fitting the linear regression model into it. Okay, so there is a process which is involved, which is working in the background, and that is giving us the best values for W0 and Wi's. Okay, and once we get that, then this is a linear regression model. Okay, fine. Now what we do for logistic regression is just take this H, X, W and plug that here. All right, so linear regression, that's the relationship between the linear regression and logistic regression, right? It's just a linear regression thing, but it has been plugged into this here, right? What do we have? We have logistic regression as logistic function as 1 divided by 1 plus e to the power minus t, right? So in place of t, we will put this h. All right, so it will be 1 divided by 1 plus e raised to the power minus h, x, and w. That's the logistic regression, right? And this is what we want to learn. We want to learn the probability, right, of the x being the positive label. Okay, sometimes I make things more difficult to understand. Sometimes I try to make it very simple. Let's see what I'm doing here. So the best would be to read and make sure that I discuss these things here. Logistic for classification, right? To extend the logistic function to m variable and set the threshold and steepness parameter of it. I believe I explained it better than what I have here. Let me know if you have any questions, right? If you want to know more in detail, you're welcome to discuss with me in my office also. If needed, I'll explain more, right? So that is the link. That is the reason why we call logistic regression this classifier as logistic regression, right? Logistic function, and in that function, the t term that we have is being replaced by the regression term. All right. Okay. And training examples are labeled as being either class 0 or 1, right? Which we are anyway doing it. We cannot apply logistic regression unless we do that formatting on the data. Formatting means the target should be changed to 0 and 1. 1 for the positive class, 0 for the negative class. Now, once we have done that, and once we decided like what our fx is going to be, then we seek to identify the coefficients w that give the high probability on the positive class item, right? And no low probability on the negative class item. So what does it mean? It means that in this learning process where we have to ultimately learn w's, right? We are not learning x because x is something that we are getting from the data. We need to find w's, w0, w1 and all that, okay, so that we can come up with the equation of a line. Now, for the logistic regression, actually, what we will have to do is we need to find out w's in such a way that if the person is, or if the data that we are feeding it for learning happens to be a positive class, that means if the data on which we are learning w is a female, for our example, then the probability should be higher, right? And if that label is otherwise, if that data happens to be a male, then the probability should be 0. So that is what we have to learn, the probability of the positive class. Okay, if the probability is lower than 0.5, then yeah, we would say that, okay, fine, this is not the positive class, this is in fact the negative class. All right, so now fine, this was the intuition. I'll assume that this is making some sense. The most important thing is to come up with the cost function, right? So that cost function is not going to work. What do you think? Can I use the cost function j, which I had for linear regression in the logistic regression? What do you people think? Can I use that? The answer is no, right? Probably it may be more complex for you to think about it. But anyway, what we should be doing straight away, let's look into the cost function, which might look a little complex initially, right? But if you spend time with it, you would find that very natural. So we need a cost function. Why? Because if you don't have the cost function, you cannot optimize, right? You must have seen that. For the linear regression also, we came up with this cost function, which was sum of squares of the residuals, right? And we wanted to minimize that. Interestingly, here we want to minimize the error arising because of misclassification, right? So the classification error is something we need to have in our formulation for the cost function. So pay attention to these plots and the terms that we have here. I'll read and then I'll explain. We want 0 error for the best probability and increasing cost as the class prediction gets more and more wrong, right? So what does it mean? Let's think about the cost associated with the positive sample, right? I have a data which is from the positive class, right? So I would determine the cost associated with what we are doing with that positive class. If the class was 1, that means positive, right? If the class was 1 and the model is also giving me 1, right, then what should be the cost associated with that, right? So the expression that we use is this one, right? Let me write it here, it will make more sense. Minus log of h, theta and x. The same point which I was mentioning to you. The problem with machine learning, and I would assume also with the data science, would be the lack of uniformity in the symbols, right? So what is the symbol here? H is usually used for hypothesis. right? So in machine learning, when we say hypothesis, then we refer to any model, right? Any model can be also termed as hypothesis, right? So we use the term H, one hypothesis. When you say H theta, then it means that a hypothesis which is described by theta vector. What is theta? Well, you could either write H theta or HW. That's the same thing. Theta means the same as the weights. All right, it is up to you whether you want to write y is equal to theta 0 plus theta 1x plus theta 2x square, or you want to write that y is equal to w0 plus w1x w2x square, right? So effectively this h theta x that you have is in fact the result that you're getting from logistic regression, right? So what does it mean? Now the cost associated with the positive class means when actually your label was 1 and you got something, right? Like what did you get? We will find out, right? So if the class label was positive and you predicted it as positive, then what is the cost? You know that log of 1 is 0. That means when the reality was the class, the data belonged to the positive class, that means when the data was for female and your classifier logistic regression also predicted as female, then the cost is 0, right? You should not be penalized because your classifier is doing the correct thing, doing the right job. Now let's think about the other extreme where the data was positive, right? The data had the label 1, but the logistic regression gave a 0, right? So here we need to find out the cost when it is minus log h theta x is giving me a 0. That's what my logistic regression is doing. So the label which was positive is being classified as 0. The label which was 1 is being classified as 0 by my logistic regression. Then what is the penalty, right? So you should know that log of 0 is minus infinity. So that means infinity, very too much of you will put a lot of cost for this misclassification, right? So that is the intuition behind this cost associated with the data sample when we know that the data sample is positive, when it's y is equal to 1, right? And what is y hat? Y hat means what you're predicting is h theta of x. All right, okay, fine. So let's have a look at this thing, right? Like when do we, how is this thing going? So h theta 0, this is what is being predicted, okay? So what will happen? This is when the reality is 1, when we know that the real label is 1, but what h theta is doing is giving a 0 for that. So look at the cost. It's not touching it here, right? So it will probably go this way and may touch at infinity. So we will penalize it heavily. But if it was 1 and you predicted it 1, then see the cost. This is 0. All right. Now let's think about the other class, which is the 0 class, when the data sample belongs to a female. So if you followed this logic, then you can easily follow this one, and you can easily follow this one as well. So let me write that here. Reality is that y is equal to 0, okay? And then the cost associated with that is minus log of 1 minus h theta x, directly correlated with this one. If you followed this one, you can easily follow the other case as well. Okay, so now when the reality is that the data belongs to the class 0, which means it is male, and you also got this value as 0, right? So you're getting exactly what you're getting, the exactly the same result. Then if you simplify it, then it will be minus log of 1, and you know log of 1 is 0. Okay, so for correctly classifying 0 as 0, there is no cost associated. That should be the case. But if in place of 0 you are saying that this is 1, then see the same thing. it will be minus log of 1 minus 1, which is minus log of 0, and log of 0 is infinity. All right, so log of 0 is minus infinity, I would say. Right, so here also it should be minus infinity, minus minus cancels out. Okay, so the same thing applies to the other class as well, and that's what you would see in this plot. All right, when it was 0 and you said it is a 0, cost is right here 0, but when it is 0, the red curve, right, and you're saying that this is 1, look at the cost, infinity. All right, all right, so let's move on. Right, so this slide that I have here is the explanation of what you saw in the previous slide, which says that log of 1 is 0. Thus, it gives proper cost for correct prediction of the positive item, right? And observe that log of 0 is minus infinity. So the cost function, what is this cost function? It says that the cost for xi when the reality is 1, right? When the reality is 1 is minus log of f of xi. Again, too many terms we are using. S theta xi, you can use S theta as well. All right, so this is minus log of whatever prediction you're doing when the reality is that it is the label 1. For negative instance, it's just minus negative c. We have 0 here. Cost for xi, when we know the reality is 0, is minus log of 1 minus f of xi. All right, so this again is h theta of x. All right, more complex thing, right? What we are doing here in this expression, that this should be my last slide for today, and hopefully I will restart from the same slide in our next meeting. Now here what you saw were two different expressions for cost. One cost which is associated with the positive label, which is y is equal to 1. The other expression is the cost associated with the negative label. What these people have smartly done is that in this one expression here, they combine these two, right? So let's do it right quickly, and then I'll explain this again in the next meeting. We can use 0 and 1 label as indicator variable to compute the loss function, right? So JW, familiar term J, 1 by n, we had 1 by 2n, we'll be fine with not having 2 here. Then what do we have here? We want to add the cost associated with each data point. We have n data point, I starting with 1 to I goes to n. There are n samples, right, which we are using for training. And now we need to see how well our model is doing in the learning process so that we could, optimize that. So the cost with fxiw, this is what? Prediction, what you're predicting, y hat, right? That is the easiest thing to do. I mean, predictions are usually denoted by a hat on that, right? So fxiw means what your model is learning, what our linear regression is learning. Okay, so the cost associated with what is being predicted and what is the reality yi, right? So this is a general term, but if you want to put what these things are, then it boils down to this thing, right? Minus 1 by n, summation is the same thing. Minus sign is coming from here. See, this is minus, so we are taking that minus sign outside in this bracket, right? Then for all these samples, right, 1 to n, this term that you have is for the positive thing when yi is equal to 1. When yi is equal to 1, this expression will kick in. And when yi is equal to 0, then this expression will kick in. Right? So if you spend time on this, then you'll realize that how smart these machine learning people are. How beautifully they could, combine these two terms together in one loss function, right? Yi multiplied by log of fxiw, which is the cost when the reality was a positive class, and now it depends like what did you predict. Similarly, this is the cost associated with the case where the real label is 0, but now it depends like what did you predict. Okay, if you spend some time, you will realize that, you know, when yi is equal to 0, then definitely this term would be gone, right? We are multiplying by yi, so only this term would remain. And when yi is equal to 1, then 1 minus 1, this term would be gone, and we are only considering the positive term. So let me stop right here and leave you people thinking on this, right? Or else I'll see you next time on Thursday. All right. Thank you so much. See you later.